Today we're going to discuss the three-dimensional structure of molecules. This molecule here is a chemotherapeutic, an anti-cancer drug. MTX for short. It works as a drug by binding to an enzyme that is involved in DNA synthesis, and so it stops DNA synthesis, killing the cancer cell. MTX binds to that enzyme by all kinds of interactions between functional groups on the drug and the enzyme. So these functional groups are enormously important for this drug functioning properly. Some functional groups that you see on this molecule are amines, carboxylates, and heterocycles. In organic chemistry, there is an enormously wide range of functional groups, all important for giving certain properties to a molecule. There are really polar groups such as carboxylates, ammonium, these phosphate esters that are also in DNA, but also alcohols and amines. These are groups that either have a charge or that can make hydrogen bonds. On the other side of the spectrum are really apolar functional groups, such as alkanes, alkenes, and benzene groups. These are typically not charged and contain mostly hydrogen and carbon. Apart from functional groups, also the three-dimensional structure of a molecule is enormously important. Here's a drug that has a sulfoxide functional group in it. Here on the right is that same molecule, but now the three-dimensional structure. What you can see is that this sulfoxide has a very peculiar and a bit unexpected three-dimensional structure. There is a very simple way of predicting that structure, and it's a combination of two types of theory. One is Lewis theory. This is a very simple theory that helps us to draw 2D molecules. The second one is something called VSEPR. This helps to convert a 2D structure into a 3D structure. What is Lewis theory? Lewis theory helps us to make bonds between atoms in a molecule by filling up the valence electron shells of the atoms. Take for instance water, H2O. In the water molecule, you can discern two types of electron pairs, lone pairs and bonding pairs. On oxygen, there are two lone pairs. There are bonding pairs that make covalent bonds between atoms. When we want to derive molecular structure from the formula of a molecule using Lewis theory, what we do is we fill the valence shells around central atoms, typically to accommodate 8 electrons. This is something known as the octet rule. As a starting point, we need to know how many valence electrons there are per atom. What you can see here in this table is that, for instance, carbon has 4, nitrogen has 5, oxygen has 6. We then determine the total number of valence electrons in a molecule and add and subtract electrons for charge. We then draw the molecular skeleton with single bonds representing 2 electrons each. We add the remaining electrons as lone pairs and reshuffle these pairs to make double and triple bonds. In the end, we can also determine formal charges on atoms depending on their deviation from the number of valence electrons. A leading principle in this is something known as the octet rule. Most elements want a total of 8 valence electrons in bonds and lone pairs around them. There are exceptions though. Hydrogen wants only 2, boron wants 6, and the heavier elements such as sulfur, phosphorus, and chloride, bromide, iodide, these can have more than 8 electrons around them. With this, we can now determine the structure of this sulfoxide in the drug that we just discussed. Using this simplified model, we determine the number of valence electrons to be 14 and then draw in bonds and lone pairs. That gets us to 2 possible structures. These are 2 representations of the same molecule called resonance structures. On the central sulfur atom, We get 2 single bonds, a double bond, and a lone pair. We can now start to use that knowledge to determine the 3-dimensional structure of that sulfoxide group using a theory called valence shell electron repulsion theory. In VSEPR, we consider the number of electron groups around a central atom. An electron group is either a lone pair or a bond, which can be a single bond but also a double or triple bond. VSEPR's theory states that these electron groups want to be as far away from each other as possible on account of the repulsion between negative charges of electrons. Around this central sulfur atom, we have 4 electron groups, 3 bonding groups, and 1 time a lone pair. 4 groups around a central atom will always take a tetrahedral geometry. So when we draw that, we get a tetrahedral geometry with the 3 bonds taking up the 3 corners of the tetrahedron and the lone pair taking up the 4th corner. When we draw that in 3D, we end up with the structure as it is drawn here. Now, depending on the 3-dimensional arrangement of atoms in a molecule, we can have different molecules, so-called isomers. This is important because different isomers can have very different properties. To determine the type of isomer that you have, you can walk through a scheme like this. The first question is, do the 2 molecules I'm looking at have the same molecular formula? If they don't, they're not isomers. If they do, they are. The next question is, do they have the same connectivity? Are all the atoms connected to each other in the same way? If not, they're called constitutional isomers. These are simply different molecules that so happen to have the same molecular formula. If they do, we call them stereoisomers. Then the next question is, are these 2 stereoisomers mirror images of each other? If they are called enantiomers. And if they are not, they are called diastereoisomers. Diastereoisomers have different physical properties. Enantiomers do not, but can still have different properties through interactions with proteins in the body. For instance, here we have 2 enantiomers that have a very different smell.